Okay, now from quantum mechanics we will move toward the field mechanics. Okay. As I have already explained that the solution of Kg equation, Kelvin-Gordon equation is solution of Kg equation is a scalar field. Okay. So if we move from quantum mechanics to quantum field theory, instead of considering the position component q and q dot, okay, we consider that field that is function of x and position. Okay, we know that this means dot means time derivative. Okay, dot means time derivative. Our Lagrangian, that will be function of q dot, as we know that our Lagrangian is a function of position and velocity, that will move toward, because we quantum field theory, quantum before moving from quantum quantization, no, we are not doing the quantization. पहले हम बिल्कुल सिंपल पे जा रहे हैं, ठीक है, क्वांटाइजेशन पे नहीं जा रहे. Firstly, we define the scalar field and then we will define classical field. So not quantum mechanics. We are moving from quantum mechanics to quantum field theory, but firstly we moving from classical mechanics to field theory. This here we are not using the operators. Okay, when we convert it into operators, then that will be a quantum field theory. Okay, now for time being we are moving from classical mechanics to field theory. In field means these are discrete number, means discrete number means these are countable numbers, 1, 2, 3, 4. So position x1, x2, x3, x4, x5. If there are n number of particles in a discrete form, then that will be a classical that will be classical particles. But if we consider that are moving, that are changing in a space-time, continuously changing, that is the function of position, that will be defined as a field. Yes? Got it? Okay. So velocity will be changed with this. Here, as we know that, actually I must write is in the form of Tx. Actually, we usually write T first and then X. Yes? Okay. So, this will move from here Lagrangian was function of position and velocity. Here Lagrangian will be function of phi dot. Okay? Yes? Got it? Okay. That will be equal to this. But for relativistic, because we are in advanced quantum mechanics, we deal with the relativistic field. Actually, they may be moving with faster speed as the speed as compared to the so fast that its speed can be compared with the speed of light. Okay, so relativistic effect will be appear. So if we consider the but for relativistic field, classical mechanics to field theory. Okay, but for relativistic field, हेलो मेरा ख्याल है फोकस ही है ठीक है okay for relativistic field your Lagrangian that will be function of phi dot for relativistic there will be not only Lagrangian that will be not only because time and velocity will be treated on an equal footage. So there will be a time derivative as well as the derivative of dx phi. Now Lagrangian will be function of phi dot. What is phi dot? That is time derivative. The function of phi, derivative of time, derivative of phi. If this dx is actually, you may say that d phi over dy, d phi over dz. So this will be function of phi t x y z. Or you may say that L is function of phi or we may write in this x bar mean x y z. I have already explained it. So this may be right in this way. So now the phi is function of phi, partial derivative of phi with respect to time, or you may say that this L is function of phi dot phi dash. Phi dash means derivative with respect to x, y, z, and dot means derivative with respect to t. Okay. By combining this, you may say that the phi is function of partial mu phi. Yeah, partial alpha. That depends upon what the terminology is. Partial alpha. Alpha mean alpha is 4 vectors 0, 1, 2, 3. Okay. Okay. Got it? Simple. Means your Lagrangian will be function of phi and the fourth velocity. Why? Now not only time will be included, but their time derivative will, position derivative will be involved. Okay, so that will be equal to this. Okay, so This will be your Lagrangian. So what is the Hamilton principle for relativistic field? Okay, what is the Hamilton principle for relativistic field? What is the Hamilton? Firstly, you must know what is the Hamilton principle. What is the Hamilton principle? Action must be stationary. Must be stationary, mean change in action, that must be a 0. Okay. S. Action must be a stationary. Yes. What is the action? Action must be stationary. Okay, it must be a globally stationary only. What is the meaning of this? What is the action? Sorry. Now, what is the action? Now, question is what is the action? Yes. Yes. Line integral of Lagrangian is defined action. Lagrangian with respect to time is defined as action. So action will be dt. This will be action. Okay. Now question, why I have used the t? Because the integration with respect to t, it means action is functional of time. Mean time will be treated as a dummy variable. Mean because we are taking that is not depending upon because. And you know what is the meaning of functional? Functional means it will be not a split function of time. Mean that will be independent from the time. Splitly. Okay. Mean time will be treated as a dummy variable. The result will be free from the time. Okay. I have already explained it in my previous lecture. Okay. What is the physical meaning? Meaning that action must be stationary. And that's the question, actual question. Why every particle Yes. If we draw a graph between position and time, okay, firstly I'm considering the classical particle, okay, not a field, okay, to understand it. If electron is, if some particle is moving from if we know the initial and final point, okay, yes, we know the electron, sorry, any classical particle when some particle, when something move in, they may choose any path. Yes, path may be anything. Okay. Yes. So we know that there is any condition on the path for traveling. We know that initially it starts the traveling from here and reach at T1. It is T1. It was at T0 that was S0, and at T2 that was so we may say that initially it starts from this was T0, S0, and he reached this is the final and TX. Okay, so we know only about the initial and final destination, and what path will be classically particle will be choose? क्या condition है classically particle के move करने के लिए? Okay. If that is initial state and this is final, which path will it be travel? Yes. Yes. Any path. There is no condition on a path because you may be move anywhere. Okay. But you know that initially you was here and finally you was here. But which path you have chosen, no one can predict. But there is some condition. Yes. That condition is that if at one time he will be at one point, not 2 points. And the path will be always continuous. So distortion in this path, that will be a path may be anything, but distortion between actual path and other path, that will be a 0. Yes, got it? No. I have already explained work done for closed path is not 0. So that is the different discussion. Okay. But it is not about the closed path, not work about not work. I am discussing only the traveling. If someone is moving along any path, then that path will be a continuous. Means if he is traveling, he moves here and here and here, but it will be at one point at one time. He will not at 2 points. Means there may be a different path. Okay. But he may not jump to from here to here or here to here. Okay. Because this will be this. You can't say that at 2 p.m. he was here and he was here too. Because, okay, and he can't be jump into the other point. He will continuously. He start moving continuously. So distortion between path will be a 0. So if line integral always represent the path along the time. If you are taking line integral along the time, the path along the time. Okay. changing of the path along the time. If there is a change in action, then path will be changed. If there is a change in a path, okay, there is no change in original path. There will be only one original path. In finite number of paths, the only one path will be original. Remaining all will be a fate. So the variation in the path will be yes, that will be 0. Means this represent the change. Okay, so variation will be variation in action that representing by the path, that will be 0. Okay, that is the physical meaning of this Hamilton principle. Okay, got it? Line integral of Lagrangian with respect to time, any path along the time, Lagrange change in Lagrange, that will be a 0. Okay, that means they will remain on their own path, at one path. They will not travel on two paths, or there will be no distortion. And some people say that these action principle is the some people. I have written that action must be stationary. I use the term the action must be stationary. Maybe some teachers use the words action, least action, yeah, action must be a minimum, action must be a least, such kind of words. That is totally wrong. Formally, that is technically that is totally wrong, because variation in path is 0, represent the first derivative. And first derivative always represent the stationary point. The change in neighborhood will be a 0. Second derivative tells about that is maximum or minimum. Because there is no condition on a second derivative, that's why we can't say that is the action will be a maxima or minima, such kind of word. That will be, I think, that will be wrong. Okay? Yes? So action must be stationary, not minimum, not maximum. Okay? Got it? So that's condition. So action will be a 0. Okay? So this is the physical interpretation of this. Okay. And what is the other condition? Initially and finally and final point, there is a two condition. And at boundary value, the problem will be a that will be a 0. So that was the physical Hamilton principle, or it is also defined as an action principle. Action principle. It is also some people now known it as it is known for some people that is action principle. Okay. Or so if delta S is 0. Yes. Yes. Delta S equal to 0, and it means what is delta S? That is change in action is dt. Yes, and that is 0. Okay, very simple. Yes. Okay. But because we are dealing with the relativistic particle, so I must represent it not t, it must travel in xy space and time. Okay, because it is so. If L is Lagrangian, yes, that is Lagrangian, L will be equal to no, this is not rho, this is L, but this is capital L and this is tilt L. Yeah, sometimes you write as LOV. Yeah, that type of L. Okay, I think now it is very easy to understand. लोगों को ये लफ्ज़ ज़्यादा पसंद है, ठीक है ना, इसलिए ज़्यादा अच्छे तरीके से. This is L. Okay. Lagrangian per unit volume will be defined as a okay. This L may be right in the form of Lagrangian density. Okay, and this will be equal to this. Okay. So now your action principle become, yes, that is 0. V volume in x, y, z, t. This will be as density will be also function of phi dt. Okay, and this may write this is a 4 integral, mean time integral as well as the x1 x. So this will become a okay. This is x4 mean dx4 means alpha. You made it. That's yes. That's and this is always depend upon your choice. Okay. No, you may use this. Okay. Okay. Now it's okay. 3 volume, 1 time, 4 dimension. Volume dx dy dz 3 उधर 4. Okay. Actually, I need a large space, white space, so that's why I must erase it. Okay. Okay. Always keep in mind this is dx. Sorry, this is dx4. This is dt, dx, dy, dz. These are multiplied. This is not equal to dx mu. That is different and that is different. Dx, not this dx alpha. Why? Dx alpha is a different thing. That is dt, dx, dy, dz. You must know this difference. dx4 means they are multiplied, and dx alpha means dt, dx, dy, dz, as I have already explained in my previous lecture for. Where I have changed it? This dx4. No, dx4 means they are 4 dimensional in space. The x as x alpha mean not position. That means t, x, y, z. Or you may say that this is t, x. Actually, space component is right x bar. Here, this is x4 means this is actually x bar, dx, dy, dz. Okay. T is multiplying, and dx4 means dt, not only space. This means dx bar. Dx means dx by dz. Well, these are multiplied. Okay. And dx4 means this, and dx alpha means that is different. Mu or alpha means that will be dt, dx. Dx. That is different. This is a 4 vector notation, and this is here. These are multiplying. These are not 4 vector notation. You must know that there is a some difference. You must note this difference. dx4 means multiplication, and dx alpha means dx mu means dt and dx. Okay. Okay. So. dx4, okay. Delta L will be equal to, yes. What will be equal to, what will be the result of this? Yes, not this. This is not delta L. Yes, this was love wala. Yes, partial L over phi, yes, derivative with d phi plus okay. And yes, we made in yes, yeah. I shifted it into the. Because this is a differential operator. Variation, change d. You may say that this is change d, derivative. Okay, this will be equal to this. Okay. Why this is, as we know that if alpha, beta, f is function of alpha, beta, df will be equal to partial f over partial alpha, d alpha plus partial f over partial beta, d beta. Okay, the same rule I have applied here. Okay, partial L over partial phi, d phi, partial L over partial this and this. Got it? D will be used here in this. Okay? They are the same. They are identical. The little bit difference is that this is not infinitesimal small. If this change approach to 0, the same formulas will be applied. That is like a D. You may write in the form of D. That is the difference. Okay? So that is like a derivative. Variation derivative. Okay. So BX4. Okay. Consider this term. If you are using alpha, you may use the alpha. Notation is by choice. There's a, I mean, you may use alpha, mu, whatever you are interested to use. Okay. Alpha and alpha, yes. This is alpha, this is alpha. This alpha is contravariant, okay, because it is a denominator. This alpha is covariant. This alpha is contravariant because it is in a denominator. Covariant, if covariant is in denominator, they will be contravariant. If covariant at nominator, they will be a covariant. So contravariant and covariant. So it is contracting with each other. Okay. So these are the main bases. Okay. Okay. If we consider that alpha is 0, alpha have a 4 value, that is 0, 1, 2, 3. Or you may say that alpha has 2 values, 0 and I. I mean 1, 2, 3, as I have. So if alpha is 0, the time derivative with respect to, not mean time derivative, then that will be a time. Okay. This will be phi dot. Yes, this will be a phi dot plus, because this is dummy means there will be a summation. Okay, phi dot, and this means derivative with respect to x. Okay. dx4 means dx multiplied with the dt. Okay. By integrating by parts, first function, if I say that this is first, this is second, okay, and I am integrating with respect to time, okay, only time, because here is a time derivativism, okay. So integration, this integration will remain the same, position integration will be remain the same. Yes, first function as it, because I am integrating with respect to t, not x, okay. This will be equal to this. This is derivative with respect to time, and integration we are taking with respect to time. So integration will be cancelled. So this will remain the same. The time integration will be cancelled. So phi. They interchange. They may be half. As I have already d by dt, may write as d by dt. I use this formula. Okay. So I have directly integrated. Okay. Got it? Acha. Okay. What is limit? T naught to t plus minus, sorry, integration with respect to time, because we are taking integration with partial derivative with respect to time, क्योंकि integration is with respect to time, of first function derivative of first function, integration of second. Because this was integration with respect to time, this, and this was dt was dx is multiplied. Yes. Okay. I know this is little bit difficult. Okay. Initial value and final, variation is at initial and variation at final, that is locally zero. Phi x at t naught initially. So this phi at x t naught initially and phi x at T final. Both are 0. Initial and final 0. So this term become a 0. Okay. Now for same will be true for the second term. Okay. But T will be replaced with the x prime. Okay. And similarly, not phi dot, here will be a phi prime, partial phi prime. Now instead of dt, here will be a dx3, dx3. Okay, you may say that this is dx3. Okay, and here we was integrating with respect to t. Now we will integrate with respect to x. The same result will become, okay, I think I must. Here the integration will be, t will become out, sorry. So here will be x naught to x. Now we have integrated with respect to x. Okay. And same at boundary. That is initial point and final point, they will be a 0. Okay, so this will be again 0. So here, sorry, that term. If here is t, here will be a x. Okay. Got it? By yes, by combining this equal to this. Okay, that one. So if I say that this is 1, this is 2, 1 and 2 combination. Okay? If we add both 1 and 2, this means partial L over partial alpha phi it will be equal to, yes, we was considering this will be equal to minus, yes, minus will be a common, okay, and this will be equal to, yes, partial over partial t, partial phi over phi dot Okay, plus, yes, partial over partial x partial phi over partial phi dash, yes, delta phi dx. When we multiply dx with dx, 4. Okay, and this may write as minus, yes, this is summation. Both are, yes, dx, this, okay. What is this? I may write it in the form of column matrix. Okay. Column will multiply with the column. Okay. Both are positive. In denominator, they will be covariant. This will be a covariant, and this will be contravariant. In division, that will be also. So this term is equal to this. So this will be equal to this. Got it? We put this here. Yes. So this will become a delta S will become a, so this will become a partial L over partial phi. This is common. This is common to every term. That may be take a common. Okay. Minus partial alpha partial phi. This was a phi. Oh, sorry. Phi dx4. Got it? Not good. Not okay. No, okay. Notes. Okay. And this is globally 0. Since this is 0 for all delta phi dx4, so integrand will be 0. So this will be this is Euler Lagrangian equation for relativistic field. So this will be a relativistic Euler Lagrangian equation for the relativistic field.